have the fundamental equation that allows us to determine the roots of the closed loop system as a function of a gain that we apply to the system, we can see how we can study this equation. We will begin with some examples, and those examples will hopefully start shaping up your intuition. So the system we are interested with is of the kind of the following kind. We have a reference signal here. We have a logic here that we assume to be a gain k, which is a constant gain k, scalar gain, that fits into a plant g. Now, the plant g is a function of s and may include some initial controller design that have been mixed with the plant in order to produce this composite plant g, so that the output y is fed back into the system by being compared with r. As more precisely, we take the difference between r and y to fit that in our logic. Now again, k here is not necessarily the controller as a whole. Okay. Maybe the controller has also a part in G. Okay. G is like K of S times, so G of S is equal to K of S times G tilde of S. Well, this is really the plant, and that is just some initial logic, whose in this case, okay, the real controller is small k times large k, okay, and small k times large k, and my mistake. Oh, let me call this guy k tilde as well. Yes. So it's k times k tilde of s, okay, and we sort of are more or less sure that k tilde is proper, and what we do is we multiply it by some gain k to adjust the gain of the overall logic. So the equation that we will look at is 1 plus k times g of s is equal to 0. This fundamental equation is sort of the equation that drives the locus of the closed loop poles for the system, and we are interested in the roots or the solutions to the equation when the k changes. And so sometimes it's easy, sometimes it is not. Okay, we can look at some simple examples first. So one simple example would be if G is equal to, say, 1 over S. Okay, then as we close the loop, we get that we get to solve 1 plus k times 1 over s is equal to 0. Or in other terms, s plus k is equal to 0. We know therefore that s is equal to minus k will be the solution to the equation. And we can plot this in what's called a root locus plane. Okay, what is the root locus plane? It is made of a real axis and an imaginary axis. On this real axis, in that plane, we plot the locus of the closed loop poles. Okay, the locus of the closed loop poles in this case will be all the values, all the locations of the solutions to the equation 1 plus kg is equal to 0 as k changes. So we say that when k is equal to 0, the locus is 0, s equal to 0. It has a particular meaning because it is the pole of the open loop plan, and we denote it with a cross. The rest of the locus that we get by changing the values of k, in this case, corresponds to the negative real axis. And therefore what we do is we say, aha, the solution to the closed loop system, or the poles of the closed loop system, are on the negative real axis, and we show it in color as I just did. Okay. Now this is particularly simple, but it carries a lot of information already, which is to say, in the case when g of s is equal to 1 over s, once we close the loop with a scalar gain k, the system is already stabilized and it gets more and more stable as the gain k increases. Now, we could be looking at things that are a little bit more complex, okay, and repeat that exercise. So I'm going to do simple example 2. And the simple example 2 will be g of s is equal to 1 over s times s plus 1. This is the model of an electric motor. Okay, and what it is the transfer function from voltage to angular position. So what we are interested in is looking at the equation, assuming that we use only proportional control. We are interested in looking at the roots of 1 plus k over s times s plus 1 is equal to 0. Now this equation can be rewritten as s squared plus s plus k is equal to 0, or in other terms, we can write that if delta, the discriminant, is equal to 1 minus 4k, we conclude that first we have two real solutions when k is less than 1/4. Okay, and these solutions look like as follows: s1, 2 will be equal to -1 plus or minus square root of delta, which is 1 minus 4k, divided by 2. Now what happens is that as k, so we can look at the locus of these roots, okay? And if I make my root locus plane here, the two roots behave as follows. The first one, -1 plus 1, so it begins at the pole of the open loop system, which is at 0. The other one begins at -1, the pole of the open loop system, the other pole of the open loop system. And then what we can see is that as k moves from 0 to 1/4, okay, I get that this pole grows up in value this way, that pole decreases in value this way, and then the two meet about halfway, and this is when k is equal to 1/4. Indeed, when k is equal to 1/4, these two guys are the same and equal to 1/2. Indeed, that's where the discriminant becomes equal to 0. Now what happens after that? Well, when k gets greater than 1/2, 1/4, then we get that the two roots instead will be s1, 2 equals -1 plus or minus j square root of 4k minus 1 divided by 2. Now what that means that the real part of these systems, so I'm going to change slightly color, okay, I'm going to say k greater than 1/4, okay, the real part is constant, and then this quantity moves from 0 to infinity, and therefore what we have is that we have one root which goes this way, the other that goes this way. And what you can see is that having complex roots means that we will have an oscillatory component. And of course, we can start thinking about adjusting k for the particular quantities that we have discussed before for second order systems. For example, how would we adjust k to get the proper TR, the rise time, proper settling time, or the proper overshoot? Okay, and that's when the fun of the design begins. But before that, we would like to have maybe a more systematic way of drawing the roots of a closed loop system versus a game that we have chosen, given that the equations that we're going to meet are not necessarily first or second degree, but in fact will largely exceed those.